We have started the shear stress in the beam itself. Yesterday, what we have seen that, what we have discussed is that what we have discussed first, that initially when we, in our earlier classes, when we have discussed about bending stresses of a beam, bending stresses occurred in a beam resulting due to the action of external forces acting over the beam itself. You know, the beam is a prismatic bar whose prismatic bar over which the force is acting normal to the axis but not along the longitudinal axis itself. Due to the action of the forces on the normal to the axis, it creates the bending effect of the bar itself. And we have gone through in our earlier chapters the shear force and bending moment which occurs in the beam itself due to the action of these external bending moments, and the shear forces are the forces acting which is resulted in a different vertical section throughout the length of the beam and which is opposing the vertical forces, and bending moment is the summation of all the bending moments of different forces acting over the beam itself, which is normal to the axis and axis of the beam, and which includes all the external forces including distributed or pointed or uh, or angular, as well as all the reaction in force occurred from the support of the beam itself. During our last class of discussion of bending stresses, we used the bending moments that takes place in different beams in order to find out the in bending stresses which takes place in the different beam itself. We have discussed that the shear stress or vertical stresses which resulted in different cross section of the beam itself is too small for to be neglected for the bending stresses. But in practice, what we have seen that the shear stress in lot of cases had lot of applications in terms of the bending stresses as well as shear stresses over the axis of the beam. And due to the action of the external shear stresses at different section, shear forces created at different sections, shear stress is also resulted in different section which acts differently than that of the bending forces, and we are supposed to know them in order to complete our design of the beam perfectly. Now, how we have calculated the shear stresses? How we have calculated the shear stresses? Uh, what we have done here, we have gone through we have from our said beam under consideration, we have taken two sections which is away from each other from an infinitesimally small distance dx, and we have gone through the bending moment and shear force acting over the section AB and a change in the bending moment acting over the portion CD, where both shear force has changed, shear bending moment is changing from S to delta S plus delta S from A to C, and bending moment from M to M plus delta M for the section B D itself. Now, we have used the bending moment equation. I mean the equation of bending stresses, that is mi by I delta sigma by E, where sigma is the stress induced, and put the value of sigma apply this equation in both section AB and CD, where this equation becomes sigma equal to m by y into y, and for AB section, and for the CD section becomes sigma plus d sigma plus m plus dm by I into y itself. Just 1 second. Next is now next from this equation of bending moments, equation of bending, we got the shear stress across both the sections AB and CD. And now we know the forces across AB will, where we have to, if we want to calculate the force across AB, we have to calculate the stress multiplied by the area itself. We thought that area of the section A is equal to A. So the force acting on AB is M by Y plus A into A, Y into A. Similarly, as it is a of same cross section, area is remains same for both AB and CD section. So for the section CD, this force becomes M plus D delta M by I plus My into A. Now the net unbalanced forces created in the strip due to the action of additional external bending moment, external shear force is like just the difference between these two equations we have formed and resulting in this unbalanced force as dm by I is equal to y into a. The total unbalanced force about the neutral axis we can find out by integrating the upward equation from the 0 to t by 2 or depth, half of the depth, because we are, as it is a, we have noticed that is a symmetrical beam. So the neutral axis is going through the central axis of the beam, and half of the distance of the half of the depth of the beam is equal to, we can safely understand, calculate the stress if we can integrate between half of the section of the beam, because other half is exactly replica of the two. So if we make the integration, and we'll have dm and I outside the point of integration, and integration is takes place from 0 to d by 2 a y dy, a for area, y is the distance of a particular strip for any horizontal strip parallel to the neutral surface. Then a y dy is equal to, is resulted in a capital A into y. Capital A into y, where capital is the total area of the beam above the neutral axis, means half of the area of the beam, y dash distance of the CG of the area of the beam above the neutral axis and to the neutral axis itself. We know that intensity, thus we have got the difference in the force created in a particular in between two adjacent section. And now to get the intensity of the shear stress we have to divide that total difference in force by the area concerned. Well, so what we are doing, total force we have put down here, dm by I, a into y, and we divide it. The dx is the distance between them, and b is the distance between the two adjacent beam, and b is the breadth, b is the width of the beam itself, or breadth or width of the beam itself. The dx into dx multiplied by b, this, so you have to divide it dm by I, a into y bar divided by dx into b itself. Dm, so it is reduced to dm by dx a y bar I into b, or f itself a y bar by ib, where because we know the differentiation of the bending moment with respect to the distance x is equal to the shear force as per our theory of bending moment itself. So we have got an equation sigma, that shear stress acting over a section of the beam is given by the shear force reacting over the section itself, and multiplied by the cross section area, and y bar is multiplied by y bar. Y bar is the distance of the CG of the area of the beam above the shear force divided by moment of inertia of the full beam itself multiplied by the width or breadth of the beam, itself. So how we have to go through? We have reduced an equation. We have to go through. We have to know how the shear force is distributed. When we so far we have discussed the shear stresses and shear forces acting between from the neutral axis to the upper portion of the beam of the neutral axis itself. So here, the value of shear stress any section, we have to calculate the distribution vector along the full depth of the beam itself. Now, for doing so, we calculate the intensity of shear stress at the important section of the beam and then sketch a shear stress diagram. Such a diagram helps us to determine the value of shear stress at any section of the at any section along the depth of the beam itself. Now, consider a beam of rectangular section here. Consider a beam of rectangular section here, A, B, C, D. It is a particular section. It is a particular section, and it is not two adjacent section which is away by infinitesimal distance dx. It is a particular section given by A, B, C, and D, and whose width is equal to the width of the beam, and whose depth of the is equal to the depth of the beam itself. Actually, it is rectangular in cross section. Now we know that shear stress at a layer JK, we have picked up a layer JK here, which is away from the shear plane, from the neutral plane by an amount Y. We have reduced this. It is given, shear stress is given by sigma F into A into Y bar divided by I into B, where F shear stress acting over this section ABCD as per our shear stress diagram, shear force diagram. A, area of the cross section of the section. Y, the area of the section Y, which is defined by the distance Y at a distance Y from the neutral axis itself, which is equal to AJKD. Now, Y bar is the distance of the shaded area. As per our just this discussion, it is the distance of the shaded area from the neutral axis. So, different of the center of gravity of the shaded area from the neutral axis of this particular section itself. And I is the moment of inertia of the whole section here, about its neutral axis, and D is the width and D is the depth. So what we are going on now, we know that the area of this shaded portion, AG is equal to area of the shaded portion AJKD is equal to width of the beam, multiplied by the depth of this section. Depth is equal to D by 2 minus Y itself. D by 2 is the depth from here to here, and Y is the depth from here to here. This is the neutral axis. So difference between these two depths gives you the depth of the section ADKJ. So as area becomes B into D by 2 minus Y, then what is the area of Y bar, which is the distance of the center of this particular section of beam sectional portion from the neutral axis itself. Y bar is equal to Y plus half into D by 2 minus Y. Y bar is equal to Y. This is Y plus half multiplied by the distance, which is already calculated D by 2 minus Y. So Y minus D by 4 minus Y, or half Y, half multiplied by Y plus D by 2. Now we have got the value of Y and we have got the value of A itself, Y bar and A. We put the value of force F, shear force acting in that section, and put the value of A, which is given in this section, B into D by 2 minus Y plus half, and put the value of Y dash, which is half Y into D by Y plus D by 2 divided by I, and F by I, D square by 4 minus Y square. We know that above equation, the above equation increases as Y decreases. This as Y is the difference from D square by 4. Lower the Y, shear stress will be higher. So it is very clear that Y is the distance of the section from the neutral axis. So closer the axis, closer this section from to the neutral axis, it will be shear stress going to be higher and higher. And when y is equal to 0, when uh, y is equal to d by 2 equal to the outermost section of the beam, tau will become equal to 0. So there is no shear stress at the outermost section of the beam, unlike bending stresses. And tau is maximum, y is 0, which is equal to the variation with respect to is a parabola at variation of tau with respect to a parabola at neutral axis. Value of tau is maximum, which is equal to tau max. You put the value of moment of inertia about the neutral of the rectangular beam about the neutral axis, bd cube divided by 12 and d square by 4, and after simplification it become 1.5 tau average itself, where 3 by 2 f by bd, bd is the cross-section area of this portion, and f by bd is the tau average tau force across the section itself. Now the shear force diagram is shown here. Here it is 0 at the topmost portion, and here it is 0 at the bottommost portion, and maximum at the neutral axis, which is lying through the central axis of the beam, as it is a rectangular axis itself. Now, the distribution what we have done so far, the distribution of shear stress across a rectangular cross section of the beam, rectangular cross section of a beam itself. Now we are imagining the cross section of the beam is triangular in section, triangular, not cross section. So a beam of triangular cross section A, B, and C, and height of which is height equal to h, and which base is width of the base is equal to b. We have to find out the shear stress here. The shear stress equation we know, just have beside tau is equal to f multiplied by a y bar I into b, or f is the shear force at this section, a y bar moment of the shaded area above the neutral axis. We are assuming this moment of the neutral axis is going through the CG of this triangular section, and we are considering a shaded section A, J, and K, which is away, whose side JK is away from the neutral axis by y, and whose height is equal to x. Now, the width of this, well, we have to find out the width of this section JA. If we consider these similar triangles A, J, K, and A, B, C, then what will happen? Then what will happen? Then B will be B into X, where X, B is equal to, this is the B multiplied by X divided by the H itself. So B into X from the similar triangles A, J, K, and A, B, C, the height X divided by H is equal to width B divided X divided by height X divided by H is equal to width JK divided by the width B. So this width will be B into X divided by D itself. The area of the shaded portion will be half of JK. We know half is the area of the triangle AJK, half of the base multiplied by the height XX, half BX by H multiplied by X, or is equal to BX square by 2H. So we got the area of this shaded portion equal to BX square by 2H, where X is the height of the beam itself, and H is the distance between, H is the height from here to here from the full section, and Y bar is the distance from the neutral axis is two-third into H, and two-third of this thing is going through here. This is the neutral axis somewhere here, minus 2x by 3, where x 2x by 3, where x is the height of the thickness. So the distance between this CG of this section to that of the neutral axis is given by 2h by 3 minus 2x by 3, the 2 by 3 h minus x. Now we got the value of y bar and a. we put this is in this equation and shear stress equation, like F remains the shear force acting over this section itself. This is the area of the section. This is the depth of the section divided by 2 into H, where divided by I into the width of the beam. Width is here given as bx divided by H itself. Which means this is the width bx by H itself. So after simplification, we got F by 3I, tau is equal to F by 3I into x multiplied by H minus x, or F by 3I Hx minus x square. Thus, we see that the variation of tau with respect to x is parabola, also is parabolic. We also see that as a as a point where x is equal to 0 or x is equal to h, tau is equal to 0. At the topmost point or peak point where x is equal to 0 or x is equal to h, you say tau is equal to 0. So at neutral axis where h is equal to 2 into h by 3, then put the value of 2 into h by 3 at neutral here, at x here, and this equation will take the form f into 3i plus 9h squared by 9 and 2f h cube where 227i. Or if you put the value of I as bh cube by 36, which is the moment of inertia of the triangle, 2fh squared by 27 bh cube by 36, or 8f per 3bh, or 4/3 f divided by the area itself, or 1133 tau average itself, where area is equal to b into h by 2 is the area of the triangle, conventional area of the triangle itself. Now, if we want to find out the maximum intensity of the shear force, then we have to differentiate this above equation with respect to x and equate it to 0. Then d tau by tau x 3fi hx into x squared to 0, or hx is equal to 0 or x is equal to h by 2, because 3 by ai and d tau x by ds cannot be equal to 0. So only this portion and equal to 0. So h minus 2x is equal to x, or x is equal to h by 2. If we put the value of h, means half of the depth of the triangular cross section, will have tau max equal to f by 3i h into h multiplied by h divided by h multiplied by h by 2 whole square, or f h square by 12i f h square by 12 into bh square by 36. If you make some simplification, it will become 3 into f by bh, or 2/3 f by area, or 1.5 tau average. So shear stress distribution diagram is shown in earlier figure here. Now, so far we have discussed one shear force distribution about a triangular section, as well as shear force distribution along a rectangular section. Now let us go through the distribution of shear force along an I section. What we have here, this is the I section of the beam, where B is the width of the, this is the flange, this is the this is the wave itself. This portion and this portion of the I section is defined as the wave, and this portion is defined as the depth. So this is the whole volume. This is the flange itself, and this is the wave itself. Now, overall depth of the section itself, B, the thickness of this wave, this from this, and D is the depth of this wave itself. This is the flange, this is the stem or stem itself. So this is B and this is D, and this is small b, this is the thickness of this flange of this front. So there we have got 3 dimension capital B, and total depth capital D. So in capital, we are saying the width as capital B and saying the depth of as capital D, and small d, we are saying the depth of the stem and showing the depth of the, I mean width of the stem, showing the depth of the stem itself. Now, we know that the shear stress in a layer Jk at a distance y from the neutral axis given by the same equations, tau is equal to F multiplied by A into y bar here by Ip. We have reduced for this. This is this equation for shear stress across any section, where F is the shear force acting across the section itself, A is the cross-sectional area of the section above the neutral axis, y is the distance of the cross-sectional area of CG of the cross-section area from the neutral axis, I is the moment of inertia about the neutral axis, and B is the width of the section itself. Now, first of all, we have to find out where y is greater than d and y is less than d. Where is y? What is y? We know y is the distance of our said strip from the neutral axis, and d is the depth of the flange itself, depth of this flange. So it may so happen y can be here or y can be here. So first of all, y is greater than this depth, b greater than the depth, half of the depth, and next is y is less than the half of the depth. This means that y lies in the flange as above figure. Say y, it is above the flange, it is on the flange itself, not on the wave itself. So y lies in the flange here. From here to here, y goes there, and the shaded area. So the shaded area of the flange, it becomes width b minus h by 2, capital D by 2, where D is the distance from here to here, half of the distance from here to here, then D by 2 minus the distance of this portion from here to here. That is, area is D by 2 minus y. So this is the height of this cross-section area, and width is equal to B itself. And now, this means that y lies in the flange in the above. Now, and this is the value of A, area of the shaded portion, and what is the area of the CG of this shaded portion, that is y dash, which is equal to y plus half of the height of the shaded portion, that is d by 2 minus y, we have just decided. So y plus half d by 2 minus y. Next, substituting values of A and y in our original equation of shear force, tau will be, say we have reduced A here and y here. We put A here as b, f into b, b multiplied by d by 2 minus y multiplied by y plus half d by 2 minus y. And f by 2i, this is equal reduced to d square by 4 minus y square, and this p is being omitted, is cancelled by this p, and so f divided by 2 into I into d square by 4 into d by 2, d square by 4 minus y square. Now, as we see that c increases as y decreases, so we also see that the value of tau with respect to y is a parabolic curve itself. At the upper edge of the flange, where d is equal to d by 2, the shear stress is 0. At the lower edge, where y is equal to d by 2, the shear stress becomes 8 by f by 8i into d square minus d square. When we put the value of y equal to the depth of the wave, it's half of the depth of the wave is the line of action of line of meeting of the flange as well as the wave itself, where the tau will be f by ei d square by 2 minus d square. So here we are starting from 0 and up to flange, it is reaching here. Now, when y is less than b, means y is less than d by 2. When y is y, the distance of jk, y which is distance of jk, distance jk from neutral axis is less than d by 2. It's if this section will take this particular form. This is y lies in the wave. Now, in this case, the value of a or y we have to find out for the flange itself. First of all, we have to find out this area of this particular flange, and then we have to add it to the area of this particular area. Then this initial area b multiplied by d by 2 is d by 2 minus small d by 2 is the height of this area. This is 1 multiplied by d by 2, it is the d by 2 itself plus half multiplied by half d by 2 minus d by 2, means from uh, from here the half of the distance minus half of the distance and divided by 2, or it will come somewhere here itself, somewhere here itself. So the here area multiplied by the distance multiplied by the y for this bigger flange is given by this total equation. If after simplification we get the form a b into d square minus d square by 8. Now about if we want to calculate the value of a y dash for the portion, this portion of the wave which is above the wave which is above this jk itself, then what will happen here also area will be b, this is the width divided by multiplied by the height of this portion, which is equal to d by 2 by y, d by 2 minus y. So this is the area of this particular portion of the beam itself multiplied by y, the distance from the neutral axis here to the jk, plus half of this distance, half of the height of half of this height, which is given by d by 2 d divided by 2 minus y. So y plus half in multiplied by d by 2 minus y. So b becomes so it is b by 2 into d square by 4 into minus y square. So total a square is the addition of this with this, which is equal to b plus d square minus d square by 8 plus b by 2 d square by 4 minus y square. Now if you substitute the value of a y bar in the above equation in our original equation for shear stress on a larger at the distance y from the neutral axis itself. So this we are put like this, a into y is this is the portion I put divided by I into b. This equation reduced here. This is the equation we are reduced here. Here we see that wave also tau max increases at y decreases here from here, and we see the variation of tau with respect to y in the wave is also a parabolic curve at neutral axis where y is equal to shear stress is maximum here. So maximum shear stress here will be The maximum shear stress here will be, we have to put the value of y here, and this tau max will take this particular shape. Now the shear stress at the junction of the top of the wave and bottom of the flange is given by y is equal to d by 2. If we substitute y is replaced by this thing by d by 2, it will take this particular form itself, 8i by b d square minus d square. Here it is clear the shear stress at the junction of the top portion of the wave and bottom of the flange is different from the above expression. That is when y is greater than d by 2 or when y is less than d by 2. We also see that the shear stress changes abruptly from f 8 ei d square minus d4 to 8 by ei b by e d square minus b square minus d square. Thus, the shear stress at this junction is suddenly increases by b by b amount of times. After I section is symmetrical, the shear stress distribution diagram will also be symmetrical in both these sides. From the shear stress distribution diagram, you see most of the shear stress is taken up by the wave itself because its thickness is less than the flange. It is an important factor in design of the various portion of various important structure itself. Next, we don't have the time left today. Next class we'll discuss the distribution of shearing stress over a thick section itself. Well, procedure of determining this distribution of stress over section is same, but here since section is not symmetrical about x-axis, the shear stress distribution will also not be symmetrical like this rectangular as well as triangular as well as this I-section beam itself. So we are stopping here. Our time is off. So we are ending the class. Thanks for your patience hearing and thanks for your attendance itself. Good luck for the exam next week.
Thank you, sir.
Thank you, sir.